Okay, hi everybody. This was the last lab that we did. Proteus. That's Friday. A few people missed it, so I'm going to go through it again very quickly. So let's start. So the first thing to do is start up Proteus and create a new project. And do what you like. Save it somewhere you can find it. Yeah. Next. To go back. What we're going to do is create a single-sided, generic single-sided PCB. Because we're going to make single-sided PCBs at the university. If you want to make something more complicated, then we can send out for it to be made. Okay, when Proteus starts up, you're presented with two tabs. This is for the PCB design, and the schematic is obviously for the design of your schematic. First thing we want to do is put some connectors on our board. So click on component mode, P, look for connectors, and SIL, and SIL 3 is a 3-pin connector. We'll place that somewhere on the board. I'm going to rotate, right click, and rotate anti-clockwise. Change the properties. Let's call it power. Okay. Now, this is going to be our power connector. So we need to add a few components to this. So we need some power. So we click on a power rail. We also need a ground. Usually put 2 grounds in. And it's also useful to have a bulk capacitor at the input. So let's have a look. Capacitors. And we want miniature electrolytic. You can select any one because we'll change it later. Just check the pin dimensions for the actual physical device that you're going to use. So you need to check everything before you decide which component you're going to use. This is 1.5mm pitch. So we'll place this here. And we'll have a little bulk capacitor. We'll change it to microfarads. So that's our input connector. Second thing we're going to do, we're going to have a voltage regulator. So we're going to have a 7805 voltage regulator. First thing we're going to do is go back to our power connector. I'm going to call this 12 volts. It's a 12 volt input. And what we need to do is go to design and configure the power rails. And at the moment, 12 volt isn't defined, so you have to go to new, 12 volts. And here we can say next connected to 12 volts. We'll click on our 12 volts and add and now we've got the 12 volt power network defined. This is my voltage regulator. So it's going to be 12 volts in, and 5 volts out, and the 5 volts is going to power the rest of the PCB. So let's have a look at the data sheet for the 5 volt regulator. So here we are, 1.5 amp maximum output current. Here's the pin out. It also tells it needs 0.22 microfarad at the input, and the output capacitor is just a decoupling capacitor. 0.1 microfarad will do. Any other details about this device? So here it's the output voltage line regulation, so it's input voltage. So here's our typically 5 volt output, and the input voltage is typically somewhere around a maximum input voltage is somewhere around 25 volts. So we quite happily regulate to 5 volts from a find it. Yeah. So you can have up to 35 volts input, and it will still regulate the output to 5 volts. So let's have a look. It said a 0.22 microfarad capacitor, so this is going to be my input, which is 12 volts. So I go back to put another power. This is going to be 12 volts. And this one is going to be 5 volts. Again, we need to create a new power rail. This will be 5 volts, 5 volt output. Again, go to configure power rails. It's not connected at the moment. To create a new power rail, 5 volts. Add. We also need a ground. And we need some capacitors, so we'll go back to component mode. Capacitors, and then we'll look for ceramic. Miniature ceramic, some more. Yeah, ceramic disc capacitor. Anyone will do. Again, check the pin dimensions. This was 0.22 microfarads. Microfarads. And then the output capacitor was just a decoupling capacitor. Which was 0.1 microfarads. So it's also useful to have some indication that your power supply is actually working, so we'll put an LED on here as well, so you can visually see that we have 5 volts. Let's type in LED. LED. And we could have an animated LED. So put in our LED. The LED needs a current limiting resistor. We can look at the data sheet for the LED, but typically it's a 1.8 to 2 volt voltage drop across the LED. It's 5 volts. If we limit to 10 milliamps, we need a 300 ohm resistor. So let's go to resistors. Any resistor, again check the pin dimensions. And if you want to simulate this, firstly we have to take this connector out of the simulation, exclude from simulation, because we can't simulate a connector. And then we can put some probes. The input and the output. Click on play. We should see we've got 5 volts output, 12 volt input, and our LEDs illuminating. So that's our power supply bit and input connector sorted. So the next thing we're going to do, we're going to put in the temperature sensor. So let's have a look at the TMP36 TMP sensor. I'll place this board, and let's have a look at the data sheet for TMP36. Here we have the pinouts, typical device that you can buy. This is one that we use. You can see pin 1 is supply, pin 2 is the output, and pin 3 is ground, looking from the bottom view. Other important points for this device is this graph here, which is the output voltage and temperature. So at 50 degrees C, you can see that there should be 1 volt output. And if we look further, we should be able to see typical connections for this device. Scroll down. So what does it suggest? That we have just a 0.1 microfarad capacitor, a decoupling capacitor at the input. So let's do that. So this is going to be my 5 volts here. So let's put power. This is 5 volts. Need a ground. Need an output. Let's see the generic output. Need to name this output. Call it so decoupling capacitor, component, ceramic. So this is the 0.1 microfarad capacitor. Decoupling capacitor. That's all it requires. So let's test this device. You can click on the properties of this device. We can set the current temperature to 50 volts, which is the maximum temperature that I wish to read. If I click on play, I should see that I get, well, let's put a probe on the output. According to the data sheet, 50 degrees C should result in an output voltage of 1 volt. Which it does. It's fine, so that's working okay. So we're going to use the output of this temperature sensor. Would typically go to my microcontroller or data acquisition system. So I need to amplify this to the maximum range of my A to D converter of my microcontroller, so my Arduino is 5 volts. So 50 degrees C, I have 1 volt out, so I need a gain 5. I'm going to use the non-inverting amplifier. I'm going to use AD820, which is single supply precision rail-to-rail op-amp. Single supply, because I'm only using the positive supply and ground. And I want rail-to-rail output. By that means that the output will be able to swing the supply rail or 5 volts. So let's set this device up. Let's look at the AD820 data sheet. So here we can see positive supply is pin 7, ground is going to be P4, inverting input, non-inverting input, and output. So refer to the data sheet and let's configure the device. So let's put on a power connector. It's going to be 5 volts. Ground. And then we need to configure this as a non-inverting op-amp. So the signal temp out is going to come in directly into the non-inverting terminal. So let's put that on. Temp out. Now I need to set up my resistor network. Ground. So if you remember the transfer function for the for the AD820 bring op-amp, transfer function, the non-inverting is V out over V in is equal to RF over R plus 1. V out of V in is just the ratio of the two resistors plus 1. So I need the ratio of my two resistors to be 4. Just the plus 1, I want a gain of 5. So I'm going to set this resistor to 1K. Set this resistor to 4K. And ideally, you need to use E12 standard series resistors to do this. So let's put an output on here. This is going to be my temperature. So I should have now, I could actually put a decoupling capacitor on here as well. Ideally, you should have one. Okay, 0.1 microfarads. Let's put a decoupling cap there as well. So again, let's probe the output. it should now, at 50 degrees C, 1 volt here, and I should get 5 volts. The output here, 1.92, good enough. Okay, so the last thing I need is an output connector. So normally the output for this device would probably go to an op-amp, sorry, a microcontroller or your data acquisition system. But in this case, we're just going to put it to another connector. The output's going to go to a connector. So let's look at connector. So let's put a two-way connector. So I think it's going to be this tag is going to be temperature. This tag is going to be ground. Let's exclude the connector from the simulation, otherwise it'll give. I'll show you what happens if you don't exclude it from the simulation. If I try to simulate now, you'll see that an error is thrown. It says there's no model specified for J2 because we can't simulate a connector. So exclude from the simulation. Okay, that should be everything we need. You can see there's no errors. My power supply, 5-volt regulator, display that we have 5 volts, TMP36, an amplifier, my output connector. There's no errors. So now we can move on to designing our PCB. Let's go to the PCB tab. Again, at the top left here, you can switch between your schematic capture and your PCB layout. So this blue line indicates the entire workspace, not the size of your PCB. So you need to specify your PCB. So you click on this square drawing object, and somewhere in the middle, you draw the dimensions of your PCB. Right click on it, edit the properties, and we'll call it 80, this could be too big, 80 millimeters by 15 millimeters. And then again, right click on it, change layer, and call it the board edge. So this is the edge of your PCB now. So everything, all of your components should fit within this PCB dimension. Remember, the blue line is just the entire workspace. So let's zoom in on our PCB, center it. If we click on our list of components, we can see here all of the components that have been defined in our schematic capture. First thing to do is place our connectors. So let's put our power connector on and have a look at our output connector. Again, you can decide where these go later. I'm just quickly placing them. And then we want our 7805, which is going to be somewhere close to my input connector. I've got a capacitor, 100 microfarads, again, which is going to be somewhere close to my input connector. And then I need to just double check what capacitors go. So C2 and C3. C2, we'll go with this. C3. Actually, this goes on this side. C3. Again, you can space and rotate it as you like. And then I've got an LED associated with this device. I place it. You say there's not been assigned a footprint. If you click yes, and we type in LED. It will tell us LED package, and this is the package that we want to assign that device. And now it has package defined. There's a resistor that goes with that. It's not 100k. Yeah, let's change it. It should be 300 ohms. Place that somewhere near mine. And if you want to just check what your layout looks like, you can click on 3D Visualizer, and you can get an idea of the spacing of your devices. You might remove things around a bit and space things more appropriately. That's not too bad. So let's put my TMP36 on. Again, you want to put that a distance away from the voltage regulator, so just pick up the temperature of that. 0.1 microfarad, that goes with C4. This device, 4. And then I've got my AD820 op amp. Place that somewhere here. 2 resistors. Again, place the green line. It's telling you the wiring, so you might want to rotate this. So that the wiring, you can see the green wires there. It's going to route to, the connection are nice and simple. And the other one, again, I could place this one just here. The last one is the decoupling capacitor. Just going to go here, and I'm going to rotate that again. So the wiring is a bit neater. And space everything out. You can reduce the size of your PCB. You space it out more, you got more chance of routing it first time. So, or auto routing it. Let's have a look in the visualizer, see what it looks like. That's okay. You could spend more time optimizing the space as you like. That's okay for now with the demonstration. Let's just move this away a little bit. One last thing to do is to go in here and edit the pin. Because what we want is all of these pins to be standard DIL. Standard DIL. Edit all of them. You can't select them all in one go, unfortunately, so you have to go through one at a time and change it to standard DIL pin. If you don't change it to standard DIL, when you drill out these pins or drill out these holes, there'll be no copper for you to solder to. So you need to change pad size to standard DIL. Okay, let's have one more look. I'll show you. That's the top of the board. That's the underside of the board. You can see now the pad or the copper on the bottom of the IC is much bigger. Some of these pads you could change. The pad size here looks very small, so we can actually go in and change the pad size for these components. So I think that was the capacitor. So you can go in here, edit. Edit the pin. So here you can select the pad size. You can get away with it. It might be too big. So we might have to leave it as it is. But if you can make the pad size as large as you can get away with. One last thing to do, we need to put a ground plane. So we've got the tools, power plane generator, and we want it to be ground on the bottom copper. We click OK. Now we can see that it's created a ground plane. So let's try and auto route. So let's auto route. Or something that's small, it should auto route, no problem. Let's try and get rid of this space here. So I go to edit properties. So what I've done there, it should now route. So all of these ground connectors are no longer required because the ground plane is actually the ground. So I can actually go around and delete. You should have automatically deleted these, but we can actually get rid of these ground connectors. As if we zoom in, you can see that this pin is a ground. It's actually connected to the ground plane. So we can actually remove. Actually, it should have done automatically, but it doesn't do it. Okay. One last thing is also quite important is the spacing between the tracking and the ground plane. And we really need to make that as wide as possible. Otherwise, it'll be very difficult to solder. So if we look at the relief, we change the relief. Let's even go with T15. We'll see now that the relief around the tracking is much larger now, around the pins. So we can get a bit larger. T20. Again, so there's much more space around the tracking and the pins. Also look at the boundary. So we put spacing around the boundary of the board as well. So that should be okay. Should be able to solder that. Let's have a look at the 3D visualizer. Again, that's the top of the board. This is the bottom. There should be plenty of space now around the component, so you can solder without causing a short across the ground plane and the pin. So we'll make it a bit larger. As far as we go, I'll go T40. Good. The wider you can make the boundary between the track and the ground plane, the easier it is for you to solder. That's probably good. Good enough. So save your PCB. And the last thing we need to do is create the Gerber file, which is the file that you send to the technicians, so that you can have the device PCB made. So you go to output, and then you can generate Gerber Excellent files. We'll do a check for you. Again, at the bottom here it says no design checked. So this is okay. You need to check there's a file which tells you which of these selections you need to make in order for the technicians to make your PCB. So when you're given the Gerber file option panel here, you need to just check through and check some of these components. Check with the file that's on the Moodle, or check with the technicians how they want this setup, because it might need to be imperial rather than metric. You need to check with the technicians. So again, you can save all the files into lab 6, click OK. Let's do that again because I want to show you the Gerber file. So I want to view it at the end. Previous one. So that's the Gerber file, which essentially is just a picture what the technicians can use to make either silkscreen or mill out your PCB for you. So that's it. That's a simple PCB from start to finish. Again, just take care. Make sure you put connectors on. Make sure you define all your power rails. Don't run lines or don't run wires between components. Use tabs. It makes it much neater. And also separate individual circuit components as much as possible. And you can even label them as well. So if you want to label particular zones, you can go over to the left tab here and write some text and say this is your stage. So for future reference, you know, obviously it gets more complicated. You know what each part of your circuit is actually doing. So you can label each section as well. So that's it. Hope you find it useful. And email me if you have any issues. Thank you very much.